Welcome to our last session today. We have only two papers. Okay, remember that tomorrow at 9 we will start. We will continue. Okay, with another session. So, the first talk. Okay, by Gautier. Right. So, please, whenever you want.
Yeah, so thanks and hello everyone. So I'll be talking about type-directed program transformation for constant time enforcement. This is a joint work with Frédéric Besson and Thomas Jensen. But first, let me put a bit of context. So I'll start by defining what side channel attacks. So we call side channel attacks the kind of attacks that does not uses the algorithm per se to gain information, but more uses physical property or quirks of the implementation of the algorithm. Two well-known examples are power analysis, which uses the power consumption of a machine to deduce information and secrets on the system, and cache attacks, which use the result of whether the result of an access is a hit or a miss in the cache to deduce information still about the system. One specific kind of side channel attack that we will focus in this talk is the timing attacks. So these are simply side channel attacks that use time as an attack vector. So mostly the execution time of a program. A simple example would be just a branching on a secret. In one branch we wait for 100 seconds. In the other branch we just skip. Obviously, if we can look at the execution time of this program, we can deduce the value of the secret. Fortunately, there is some mitigation possible. The first one is to take extra care when programming. So you have to take into account any possible leaks while designing the algorithm and while doing the implementation. That's a bit tedious. Another one who seems kind of obvious when looking at this example is we can try to balance both branches. So if we had a wait 100 in the else branch, whatever the value of secret is, the execution time is the same, and there is no issue. That's a bit helpful because it has been proven that if we combine timing attacks with power attacks, this solution doesn't work anymore. And one only real solution is left, that is to transform the program to abide a certain programming policy, which is the constant time policy. So as I said, the constant time policy is a programming policy to defend implementation against these specific types of timing attacks. It is based on two constraints on an implementation. First, we shall not make any control flow decision using secret data. The intuition is kind of obvious. We just have to look at the previous example. If one branch is unbalanced from the other, doing the choice between branches on a secret will leak this value. And the second constraint is no memory accesses using secret data as index. That's a little bit less obvious because it is not immediate. It is due to counter cache attacks, notably, which will use the time taken to get the information back from the cache to reduce the information on the secret. To enforce this constant time property, we have multiple solutions. So we have two solutions which are based on guaranteeing that the program is constant time. So first, we can use a verified compiler to prove that the compiler preserves the property of constant time. So if we're able to prove that the input program is constant time, the output one will be too. And the second possibility, which is often coupled with the first, is that we can prove directly that the program, whichever source or compiled, abides by the constant time policy. Both these mitigations have an example, and I have two citations here, which show that we can preserve constant time when compiling C, and that we can check that an implementation is constant time fairly easily. The other category of mitigation possible is the program transformation. So first we have the balancing that I have shown just earlier, and well, it doesn't really work. We can also use program repair, which is that we will transform the program directly in its form, so it will not pass by an intermediate language or go from source to compile, but stay in the source form. And the final category, which is the base of this work, is program transformation. So one good example is FACT, which uses a type system to compile any program typeable by accepted by the type system into a constant time equivalent. So to present a bit of this talk we go, I'll now present the usual tools used by most of these possible mitigations before presenting our proposed program transformation and its according type system before concluding, obviously. So the first of these tools is actually an operation that we use to enable ourselves to make a choice while being constant time. So we define a constant time selection, which has the same semantics that the ternary operator. So that is that if the guard C is true, then the CT select is equal to E1, else to E2. It's just a conditional in an expression. And we have the property that this particular operation is constant time. That is that whatever the value of C is, it does not leak, it takes the same time. It is not just a theoretical object, we can actually implement it. One way to do it is to use bitwise manipulation. So here we have an example, and we can go through one case. If C is true, then E1 and C will bulge down to E1, E2 and not C will bulge down to 0, and E1 or 0 will bulge down to E1. And it's exactly the same for E2, C, if C is false, and we have the correct semantics, and it is constant time. Whatever the value of C is, we evaluate both E1, C, and E2. On top of this construction, we can propose some transformation. So if we want to mitigate the no secrets access thing, one way is simply to go through all the array. It's not efficient, it's a bit naive, but it works. So if we make a memory read on a secret, we can instead make a for loop over all the array, and if the index we are looking at is the same as a secret, we make a real assignment, y is equal to t of I, else we just make a dummy assignment, y is equal to y. This only works if the array size are public, so that we can loop through without leaking the size, and if all access are initially within the bounds, because if not, we will not find I such that secret is equal to I. Unfortunately, this is incredibly inefficient. If for whatever access we have to introduce a for loop going through all the array, it's tedious, and it's even worse for complex expressions. So, for example, if we make an access on a memory access, while using a memory access as an index, we have to nest 2 of those for loops, and the complexity goes up fast. So that kind of settle how we can transform memory access. The other constraint was to secretly branch on data. Sure, we have the CT select, but we can't put a whole branch within one expression. So what we do is that we use the CT select operation to predicate statements. This is the solution most used by current work. And if we take this simple conditional, we just assign to X the value L1 or L2 depending of the guard, we can transform it into 2 assignments, each one using a CT select, and each one having the semantics of one branch. So the first one is equivalent to if X is assigned to L1, otherwise nothing, and it's the same for the second one. And overall, the semantic is the same, and because of the constant time property of the CT select, this presenting code is constant time. It does not leak anything. So these are the tools available currently, but well, some are costly, This one is a bit simplistic. Maybe we could do better. And that's actually what we have done. We propose a more permissive program transformation to constant time, which will try to use the array traversal method as less as possible. And to do so, we introduce a new typing system, which both guides and proves the correctness of the transformation. We also have a Jasmine implementation and some experiments. And the reason why we need a more permissive program transformation is because if conversion has some issues. The first one is the safety issues. If we have an access of which the safety depends strictly on the value of the guard. So for example, here, if we do not have the I less than S, we do not have any guarantee that I is within the bound of T, then applying the if conversion will still do the access whatever the value of I is, and we may do an out of band access. And the second issue is that the if conversion introduces direct flows. So if we had, to our previous example, a memory access in each branch, transforming it will yield something like this for the then branch. That is that we first predicate the assignment to X, so it works, we know it. However, when we try to make the memory access to get the value for Y, X is no secret because it is directly dependent on H, and we leak the value of H. So yeah, our goal was to mitigate these two issues, and we'll start by the second one, not the safety one. So how can we prevent the introduction of direct leaks? Well, we just postpone the introduction of direct flows. So if we take the same example, what we'll do is that we'll define new fresh variables for each branch. So xn, yzen, xelse, and yelse. You can see that the access made on xn is completely secure because we do not have any leak into xn. It's just the value of L1. And what we do to preserve the semantics is simply that we delete the condition, just as in branch removal, and we merge both branches by using a predicated statement. This way, both memory accesses are safe, and the semantic is preserved because we choose the variable which is the correct one, which is the correct branch executed. However, the code that we use as an input, it could be a bit smarter because we are doing the same memory access in both branches. What if the developer was trying to optimize and move it out of the scope of the conditional? In this way, we will have a kind of the same problem, that is that we are merging the statements too soon, because what we do is that we will merge both X that we have defined, and then only make the access on X, thus leaking the value of H. To prevent it, what we do is that we simply delay the predicated statement until after the memory access. Doing this like this doesn't work because we make an access on X and we only define xn and xelse. This doesn't make any sense. So what we do is that we rename Y also. And we also merge the value of yzen and yelse into Y. So what we do in the general case here is that we identify a leaking condition of a conditional, leaking continuation, of a conditional, and we wait until the end of this leaking continuation to introduce merging statements. And thus, with both the delayed if conversion and this scope increase transformation, we should be able to transform any secret conditional away. Remains the problem of safety. So, for a reminder, the issue was that executing both branches may cause out-of-band excesses. To prevent that we access any index out of the bounds, what we do is that we simply add dynamic checks. That is, if we have a memory access on index I, instead we do memory access on if I is within the bounds I, else 0. So this way, it is always within the bounds. Because our programs are initially safe, we know that y in the correct branch is always within the bounds, so it does not change the semantics. And if it is the wrong branch being evaluated, the transformation is smart enough to ignore the statement anyway, so it does not have any impact. We can combine these three transformations to obtain a final transformation. So the idea is that we will loop for each secret conditional. We'll find the secret conditional and identify its continuation. That will use scope increase to move the leaking code within the conditional. We'll apply our dynamic checks to ensure that safety will be preserved when we remove the conditional, and we apply finally the delayed if conversion. And we repeat this one while there is at least one secret conditional. So the idea that we will remove one secret conditional at a time. There is only a finite number of secret conditional. This will end, and no secret conditional will remain in the final program. And thanks to the delayed if conversion, we also remove most of the secret error excesses by removing the conditional this way. And just in case, we still apply a path of error traversal to ensure that there are no secret accesses left at all. And so because we have no secret conditionals and no secret accesses, the resulting program should be constant type. To actually do that, and more than anything prove that, we define a type system. So firstly, the first problem was to identify this leaking continuation and know if there are any secret conditional left without having to pass through the whole program. So to do so, we annotate programs with two sets. The first set, G, is a set of secret conditional within P, so simply the set of guards. And R is a set of conditional leaked by P. So to define this set, we use program top points. So if you can see here, we uniquely identify each conditional with a program point, and this set are a set of program points. And so G is a set of conditionals contained with the program, and R is a set of conditionals whose value is leaked by a statement. So if we still take a look at our example and try to annotate it, the first step would be to annotate the memory accesses. So they contain no guards, so G is empty, but they leak the value of X, which is dependent of H, so R contain only P. And if we annotate, the whole program, we have the same leakage, but we also have that the program is the conditional P, so it obviously contains the conditional P. And to identify the leaking continuation, what we do is we find the last statement which leaks P, and by taking all statements previous to this one, we are able to contain all possible leaking statements. To do a bit of reminder on type system and mostly secure type system. So the first one was the one proposed by Volpaner-Smith. We use two types, high for secret value and lows for public ones, which was a type insensitive type system. So a variable was either high or low and stayed so for the whole program. And it prevented assignment of secret value into public variables. This was a bit too restrictive, so it was upgraded in 2006 to be flow sensitive while keeping the same two types. So now types could be updated through the program. So assigning high values to a public variable would make this variable secret. And what we do is that we upgrade once again this type system. So because our transformation relies on preventing the introduction of direct flows, what we aim to do is differentiating between direct and indirect flows. And to do so, we extend the usual high-low lattice with a new type, IFL, which tracks indirect flows. So a type a variable is of type I of L if it indirectly depends on all conditionals whose program point is in the set L. So if we take the first example that we had, the type of X would be I of P because X is assigned within the conditional P. And to be a bit more practical about our type system, the typing judgment for an expression uses two typing environments, one for arrays, one for variables, and yields a resulting type and a set containing all conditionals linked by E. So this will be what will allow us to compute annotations for statements, because, well, for example, if we look at the typing rule for the array red, so the first thing that you notice is that the type system rejects secret accesses. We are needing that the type is an indirect of something, while we can note that an indirect of nothing is simply a public variable. So we just reject if the type is high. And when defining the leaks of the expression, we take both the leaks of the evaluation of the index and the type of the index, meaning that we leak the value of E, which is consistent with all the examples we have seen since for now. And for our statements, we keep the same structure. We just add a context, which is used to track parent conditionals. So when we enter a scope of a conditional, we upgrade this context to contain the program point of this conditional. Same, we'll look at this a bit longer typing rule for a conditional, a non-public conditional, sorry. So the first thing that you can notice is about context. What we do is that we evaluate both branches using a context which is augmented by the program point of the conditional. We also update the set of conditionals to contain this one because, obviously. And note that we do not leak the value of C like we did leak the value of the index, simply because we are sure that we could transform away the conditionals anyway. And so this type system using annotation has an interesting theorem. That is that if we take a program P which is well typed with a low context and empty annotation, then the program is constant time. This is easy to intuitionate because if we do not have anything in the annotation, that means that we do not have any I conditionals. So that means that there are no secrets possible to do array accesses on, and we do not have any I conditionals. So yeah. And we can also use this type system to have a guarantee on our transformation. That is that if we have a program P well typed and a program point P within the program, then transforming the program P by removing the conditional P, that's a lot of P, will yield a program that is also typable, but that has a guard annotation, strictly less than the initial one. So we have removed at least one conditional. And the same reasoning as earlier, there is only a finite number of conditionals, so we end up by having no conditional at all in the program. So we type without annotation. So by chaining sufficiently our transformation, we end up with a constant time program. So yeah, that is the conclusion. All programs can be constant time, well, if they are writable in our syntax. Even though I didn't talk about it here, experiments showed that the overhead is often mitigated by optimization. We introduced a lot of temporary variables, but compiler are smart enough to remove them because they are just single assignment. And for future works, the idea is to experiment with real-world example, but mostly to extend the scope of a language. So by handling function calls and looping out secret value, which we do not do here. Thanks for listening.
Questions?
So you mentioned.
So in Splash, they are recording all the talk in all the places. Okay, so the microphone is just for the recording.
Okay. You mentioned at the end that the compiler might then do some transformations and optimizations. How can you be sure that the transformation the compiler does is not the compiler is not going to undo what
if
you've
we
done?
if we use a standard compiler like GCC, then we have no guarantee. However, we also tried using CompSort, which has been proven to preserve the constant property, and Jasmine, which is a compiler built for that, and which is the compiler we use for our implementation.
Okay.
So in the general case, it does not work, but using specific compiler, we can have the guarantee that the property is preserved.
Okay, thank you.
Any other question? Yeah, I had the same comment because of the. Yeah. Well, so indeed, I was going to ask you about the next steps, which is indeed what you wrote in the perspective there. So can you tell us a little more? So I was expecting some experiments. I mean, maybe not tables, but some experiments.
Yeah.
So it's a pity that you didn't include here. And I'm not sure, I don't remember if you had in the paper or not.
There are some in the paper. We actually did experiments with some simple encrypted programs. We found out that the result is constant time, and that the overhead is at intermediate level quite high. We are our exponential is the number of variables, but after optimization passes, there is a 1 or 2 offset between the original program and the transformed one. But that's all the point with the experiment on real-world example, which will allow us to see more if this transformation really introduced lots of overheads on it.
Yeah, indeed, and that's the thing that I wanted to ask, in the sense that I mean this graphing, the algorithm kind of thing that you had, right? So the thing is that in real, in long examples, let's call it that way, right? It can be really, I mean, just the program transformation itself can really take a lot of time. It depends on the complexity of the program. So that's why I think that you need experiments in some sense to
yes, and we did on nested conditionals, and it is always linear in the number of conditionals, whatever the structure of the program is. So,
yeah. Okay. Any more questions? No? Okay, so let's thank the speaker.